Okay, dear MAE3293 students, this is a video lecture that I'm recording uh, to review what we covered recently in Chapter 3, particularly regarding the isentropic flow in a converging and diverging nozzle. Essentially, the problem there was you have a reservoir and you want to empty out the reservoir or drain the reservoir using a nozzle, and we explored how the physics would behave if you use a converging nozzle, and subsequently we also explored what would happen if we use a converging diverging nozzle to isentropically drain out the fluid. And we had some very interesting observations, and I know since you students are trying to hearing this from me for the first time, my suspicion is it's a little bit difficult to understand. So to address that, I wanted to do this this review session, which is also going to be the final discussion section that I want to have pertaining to this chapter 3. Okay, and what I'm showing here in this screen is the schematic, what you have already seen before. It's a reservoir. So this is the reservoir, and the reservoir is so this is the reservoir, and the reservoir is connected to a converging nozzle, and the reservoir has properties PR and TR, which can be approximated as P naught and T naught, the stagnation values for this isentropic flow. And the area of cross section at the exit plane in this case is AE, and let's denote the pressure and temperature, the static properties, that is the static pressure and static temperature at the exit plane, to be PE and TE. And the control parameter that we're using to drain this fluid is, in this case, is the back pressure, or the pressure in the background, denoted by PB. And the idea is that as the pressure difference in the pressure between the reservoir and the back pressure is established, the fluid can be drained through this nozzle as the fluid flow would happen, and we're going to explore how this drainage process is going to evolve for different values of the back pressure. And to do this, we are going to systematically vary this back pressure from the reservoir value, which corresponds to case 1, at which basically there is no flow. So there is basically no flow for this case, and where PB equals PE equals PR. Okay, and so the ME, which is the Mach number at the exit plane, is 0. Okay, the reason for using PB and PE is going to be apparent pretty soon if you already haven't figured this out yet. But the idea is that PB and PE are expected to be the same in most situations. PB is what is the pressure at the back end, or the atmosphere environmental pressure into which this nozzle is emptying out the fluid. And PE is the pressure at the exit plane of the nozzle. In principle and in theory, these two should be one and the same, except for some extreme circumstances, which we will talk about. Okay, and the circumstances when PE is not going to be equal to PB are going to be far and few. Okay, that's how you should view it. So now, instead of having my PB equals PR, now I reduce my PB a little bit. So now my PR is higher than PB, which means the flow is going to happen from left to right in the nozzle. And when that happens, my back pressure will be the same as the exit pressure. No reason why it should not be the same, and this will be smaller than my PR. Okay, and my ME is a much, which is the Mach number of the exit plane, is going to be a very weak value, or a very small value, say about approximately say 0.1, 0.2, depending on how small this PB or PE is. Okay, and if I reduce PB further. Now if I reduce PB, which is again going to be the same as PE, and if I reduce this further, smaller compared to PR, then my Mach number at the exit plane is going to increase further. So instead of being much smaller than 1, it is going to be smaller than 1 but a sizable value. So let's assign a number. So in this case it's approximately, say, 0.5 or 0.6 range. Okay, so it's in the vicinity of a transonic flow. And now as I decrease the back pressure further, say let me denote this back pressure for this case 4 by this guy. So again my PB equals PE, and this is going to be much smaller than PR. Then my Mach number in this case is approaching 1. Okay, so this is what is called as the limiting case, and as we all know, for a converging nozzle, the maximum Mach number that can be realized in such a shape is a value of 1 at any location, and this would occur at a location where this would occur only when at a location where dA is approximately 0. And we also know from previous analysis that that when the Mach number equals 1 at any area of cross section, then that flow represents the maximum flow rate through that cross section. And for a nozzle, we know that if that maximum flow rate occurs at the minimum cross section, then that would correspond to the maximum flow rate through this nozzle, and that's what we are observing. So what this case 4, this is case 4, okay? So this case 4 would correspond to is that the exit Mach number will be approximately equal to 1. This would occur at a region where the dA is approximately 0, which is correct, and would also occur in a region which corresponds to the smallest area of cross section in this nozzle, which means this case 4 corresponds to the state where the nozzle, this converging nozzle, has maximum possible flow rate. Okay, maximum possible flow rate for a given P naught and T naught. Okay, so this corresponds to the maximum possible flow rate. Now what happens if I reduce my PB further? So my PB is, say, 4 lesser than arrows smaller than PR, then in this case my exit Mach number will still be equal to 1, right? Because the exit Mach number can achieve only a maximum value of 1 in a converging nozzle. It cannot go beyond 1, which means my ME is still going to be nearly 1. And if my ME is still going to be nearly 1, then PE is going to be obtained from my expression for isentropic flow, which is P naught by 1 plus gamma minus 1 by 2 ME squared raised to gamma by gamma minus 1, which is P naught divided by gamma plus 1 by 2. Okay, so that is the value. So let me kind of write it this way. Okay, it's easier. So so I'm going to move this guy here, and let me write it. So this is going to be P naught divided by 1 plus gamma by 2 raised to gamma by gamma minus 1. So this is what my PE is going to be. So my PE is going to be determined from the dynamics within the nozzle, and the dynamics within the nozzle tells me that the exit Mach number can at most be 1. So my PE will correspond to this value, and this and this is the same value for PB that I had. This is the same value of PB that I had in case 4, okay? And my PB in case 5 is smaller than the value that we had in case 4, which means my PB 5 corresponding case 5 is not equals PE. Okay, so this is the reason why PB is not equal to PE in this case. There is another interpretation. When your Mach number becomes 1, the case 4 is the instant when the Mach number becomes 1, and PB will obviously be equal to PE. And when you reduce back pressure further, as in case 5, the Mach number is already 1 at the exit plane of the nozzle. And whenever you have a sonic flow, you're going to have a zone of silence that is going to be created. So which means any further reduction in back pressure on the beyond the exit plane of the nozzle is not going to be sensed by the fluid in the vicinity of the exit plane of the nozzle or inside the nozzle. And hence the reason why your exit plane pressure does not match the back pressure. Okay? So with that understanding, let us kind of move on to the converging diverging nozzle, but instead of moving on in a generic way, what we would do is we would relate it to this discussion that we just had. So what I'm going to do is the following, okay? So I'm going to take this same schematic, I'm going to paste it okay, I'm going to paste this here. So let me call this as the converging diverging nozzle case. And what I'm going to do here is the following. The way I'm going to build this converging diverging nozzle is by simply adding a diverging section or retrofitting a diverging section to, okay, I'm going to simply retrofit a diverging section to this converging nozzle, which means what I had here, what was the exit area for the converging nozzle, is now going to become the throat section in the converging diverging nozzle. Okay, and I'm going to have PE, AE, TE here. Okay, now I can erase all of this. I can erase all of this here, and let me redraw these cases again. Okay. So that is what I'm going to do here. So let me okay, and so let me retain the numbers, the case 1, case 2, case 3, and the case 4 and the case 5 numbers. Okay, so that is, those are the numbers for the converging case. Now what I'm going to do is the following. Okay, and so in this case, the consequence of retrofitting a diverging section to this converging nozzle has two effects, okay? One, potentially, in fact, there are three effects which I'm going to discuss in a minute. But the first thing that would happen is the diverging section would allow the possibility for the flow Mach number in the nozzle to go beyond m equals 1. That is kind of obvious, so you guys know this already, okay? Because in the diverging section, when you have a sonic flow, it has the potential to expand or accelerate further into a supersonic regime, okay? The other thing is the diverging section can either expand the flow or compress the flow depending on the Mach number that is coming through it. So which means it can modify the back pressure. Okay, so what was in the previous converging nozzle, so let me use another color. Let me use a blue. For converging nozzle, the back pressure was here, right? And for the converging diverging nozzle, the back pressure is here, okay? And there are some interesting possibilities that this is going to generate. And I'm going to tell you what those things are, okay? And this is kind of obvious to everyone who has paid attention so far, but this is but if you haven't, it is a good time to understand what is going on, right? So now let me take the case 1. My case 1 is what? My PB equals PR, there's no flow, so if I extend the pressure distribution in the diverging section, then this is again going to be case 1, ME equals 0, okay? PB equals PE equals PR. Basically, there is no flow. Now, let me extend the curve for the case 2. Case 2 is what? My PB is slightly smaller than PR, which means there's a small amount of flow that is being generated. And when the small amount of flow is being generated, there is a certain Mach number, but this Mach number at this throat location, which was actually the exit plane location for the converging case, and the Mach number that we estimated was about 0.1 or 0.2. So now in this case the throat Mach number is about 0.1 or 0.2, which means in the diverging section the Mach number, it's going to be a subsonic flow in the diverging section, so the flow is going to get compressed and decelerated, okay? So which means the Mach number is going to decrease here, okay? So let's look at this case 2, and the pressure is going to increase because it's a compression. So what we are going to have is ME is approximately 0.05 to 0.1. If the throat Mach number was say 0.2, say if here you can argue that say if the MT is approximately 0.1 to 0.2, then the exit Mach number is going to be 0.05 to 0.1, and my PB is going to be still equals PR, PB equals PE, and this is going to be small, just slightly smaller than PR, okay? Just slightly smaller than PR, okay? And you can even see the trend here, right? What are the two things that happen? The exit Mach number in this case is lower, right? For the subsonic flow case as compared to the converging nozzle, and the exit pressure or the back pressure is kind of higher. So in the previous converging nozzle case, the back pressure was the throat pressure in the converging diverging nozzle case. And now because of the compression, the pressure increases in the diverging section, which means my back pressure, okay, and the exit pressure is higher compared to the back pressure for the corresponding converging nozzle case. And this has strong implications from the nozzle design perspective. So if you're designing a nozzle for an environment which tends to have higher pressure in the background, and if you are interested in generating subsonic flow, then a converging diverging nozzle might be a better fit compared to a simple converging nozzle of the same size. Okay, now we can extend the same thing for the case 3. The case 3, what was the property, right? So we estimated MT, which is ME in the previous case, was about 0.5 to 0.6. Okay, so MT is approximately 0.5 to 0.6, which means it's still subsonic flow at the throat, and this flow is going to decelerate in the diverging section, and the pressure is going to get compressed further. So this is going to behave like this. So this is 3. In this case, ME will approximately be 0.3 to 0.4 range. PB equals PE is going to be it's going to be smaller than PR, but higher than what it was for the corresponding converging nozzle case. Now, if I decrease my back pressure further, okay, then but not as much as I did for the converging nozzle case, then my Mach number at the throat is going to be 1. Okay, and so if the flow, I'm sorry, it's supposed to be 1, right? The Mach number at the throat is approximately 1. And if the flow is sonic at the throat, there are two possible solutions, okay? And since and one possible solution is the flow could either accelerate into a supersonic flow regime and expand consequently, which means it will have a lower pressure compared to the pressure here, compared to the value of the pressure PT here, okay? And at PT corresponding to MT equals 1, right? Or if I have a pressure that is higher than this PT, or which is the exit pressure for the converging nozzle case, then my flow could decelerate into a subsonic flow in the diverging section, and the fluid will get compressed into a higher pressure state. Okay, so this is the reason why I said the two possibilities that can occur, and which possibility really transpires depends on what is the pressure at the back end. And in this case, since we are starting at a high value of the pressure and systematically decreasing, the pressure that we are encountering in case 4 is the higher value of the back pressure. So the pressure curve here is going to look like this. And this is going to be 4. So because the Mach number at the throat was approximately 1, which is and my PT corresponding to MT equals 1 is the same as the exit pressure. So this is going to be equal to PB4 for the converging nozzle case. Okay, so this is going to be PB4 for the converging nozzle case. Now in this case, I'm going to have, because of the diverging section, the flow is going to slow down. So my ME is approximately going to be 0.7, 0.8 range, something like that, and my PB will be equal to PE, will be much smaller than PR, okay? And this guy will also be higher, and this guy will be higher than PB4 for the converging nozzle case, which is the case that we just presented earlier. Okay, so because in this case the PB4 for the converging nozzle case is the same as the throat pressure value, which is the value here, and now the flow is actually getting compressed from the sonic flow at the throat. Now I can have another state, isentropic flow state, where if I can decrease this back pressure substantially, then what happens, right? Does the mass flow rate in this converging diverging nozzle increase any further beyond this state 4? No, because this throat location, which is the smallest cross section for this converging diverging nozzle, already has a Mach number of 1, which means by theory we know that this is the maximum possible flow rate through this nozzle. So the nozzle cannot support any more flow, which means the Mach number at the throat cannot increase any further. So the Mach number at the throat is going to be 1. And if the Mach number at the throat is going to be 1, then how the physics is going to respond is by opting for the supersonic flow solution. So let's call this as the supersonic flow solution. So in this case, the case phi is not an expansion value. In the previous converging nozzle case, the case phi was a simple expansion, a rapid expansion outside the nozzle. In this case, because of the presence of the diverging nozzle, you get a very nice gradual expansion. In this case, the Mach number is going to increase. So it will be approximately 1.8, 1.9 or whatever value. I'm just giving you representative values. And this value would depend on what AE by AT is going to be. Okay. And my back PB, okay, will be equals to PE because this is an isentropic flow solution, and we are choosing the back pressure value to match exactly the exit pressure value corresponding to the supersonic flow state. And this PB will be equals PE, and this will be very, very, very small compared to PR. Okay, typically 1/5, 1/6 of PR. Okay, and this this PB will be much smaller compared to PB5 for the converging nozzle case. Okay, now I can have, and this is the second isentropic flow solution, because there's a second solution that satisfies the criteria that for this value of AE by AT. Okay, so this is the second isentropic flow solution. This is the second isentropic flow solution corresponding to the given value of AE by AT. Okay. Now I can decrease the back pressure further. Okay, and if I can decrease the back pressure further, I could potentially, okay, I could potentially have something like this. So I could follow. So now what is happening? The flow is supersonic in the diverging section, right? So if the flow is supersonic in the diverging section, then any change in back pressure is not going to be felt by the fluid in the inside the nozzle, because for a supersonic flow, there is going to be a even smaller zone of action and a larger zone of silence, which means the information about the reduction of back pressure is not going to be propagated into the nozzle. So if I reduce back pressure further and create a case 6, then the pressure distribution inside the nozzle is going to remain the same in the form of these red dots, and just outside this outside this nozzle exit plane, the pressure is going to drop rapidly. Okay, so this is going to be the case 6. Okay, this is going to be the case 6. My ME will still be that 1.8 or 1.9, and my PE will not equal to PB in this case, because the nozzle physics cannot adjust to this back pressure. Okay, so this is the physics of the converging diverging nozzle. So there are some interesting takeaways that one can have. Let's see, let me insert, create a new page here. So there are some interesting takeaways. Okay, the first interesting takeaway is, if we were to build a set of converging and converging diverging nozzles as above, the maximum mass flow rate between those two nozzles are the same. Okay, that's the first takeaway. This is obvious, right? The maximum Mach number in the converging nozzle is ME equals 1. Okay, and that exit area in the converging nozzle, in the case of a converging diverging nozzle, happens to be the throat area. And in this case, the maximum Mach number at the throat area is going to be 1. And which means both nozzles can only support the same flow rate because in the smallest area of cross section for both the nozzles, the Mach number is 1, and the smallest area values are also the same. In the converging nozzle case, it happens to be the exit area. In the case of the converging diverging nozzle that we have designed, the throat area is the same as the exit area for the converging nozzle, right? As long as the exit area for the converging nozzle equals the throat area for the converging diverging nozzle, and P naught, T naught are the same. Okay, the second thing is for the same flow rate, okay, for the same value of Mach number, that is for the same value of Mach number at the throat for the converging diverging nozzle, or the exit for the converging nozzle, the back pressure PB is lower for the converging nozzle case as compared to the PB for the corresponding converging diverging nozzle. Okay. Okay, this is true as long as the maximum nozzle flow Mach number is 1. That is, as long as the flow doesn't become supersonic, okay, that is, flow should not be supersonic. Okay, if flow is supersonic, then this is violated, the back pressure is going to be lower. So that's kind of obvious, but that's just one of the cases. In general, as long as the flow is subsonic, this is going to be true. The third observation is for, let me kind of copy, okay, I copy some of this text, so it's just going to so for the same flow rate and for the same value of Mach number at the throat, the exit Mach number ME, that is ME in the converging diverging nozzle will be smaller than the ME in the converging nozzle. Okay, will be smaller than the ME in the converging nozzle as long as the flow is inside the nozzle is sonic or subsonic. This is obviously violated when the flow expands into a supersonic flow to supersonic speeds in the diverging section of the diverging nozzle. Okay, so these are the three observations that I wanted to make, and it'd be useful for all of you to think through these observations and make any more observations on your own if you think they are relevant. Okay, I think this is important to realize these what are the trends between the converging diverging nozzle relative to the converging nozzle operation. Okay, so with this knowledge, there is one example problem that we are yet to complete, and so I need to work on this example problem. I think this is one of the example problems from the text. So let me create a new page space to solve this problem. Okay, so the problem statement is the following: you have a converging diverging nozzle that is designed to operate isentropically to generate a supersonic outflow with Mach number 2.0. The nozzle is supplied air from a tank with pressure 600 kilopascal and a temperature of 500 Kelvin. Okay, and the throat cross-sectional area is provided. Okay, and assuming air is a perfect gas with constant Cp, gamma equals 1.4, R is 287, all of this is provided. Then the question is, find the range of back pressures Pb when the nozzle is choked, and also compute the mass flow rates through the nozzle for Pb equals 450 kilopascal and Pb equals 0 kilopascal. Okay, so this is based on the understanding that you must have developed over the past two lectures. I think this problem is a straightforward problem. So let us kind of list out the basic assumptions in this question. So obviously the first thing is PR equals P naught equals 600 kilopascal. Okay, and TR equals T naught equals 500 Kelvin. What else, right? Gamma equals 1.4 is given. R is 287. Then obviously we are assuming it's 1D steady isentropic flow, which is kind of a given at this point in this course. Isentropic flow. So the question is, ME is given, right? So what is given? ME is provided. Given AT is 0.001 meter squared, P naught equals 600, T naught equals 500 Kelvin, and what else? It says it is designed for an exit Mach number of 2.0. Okay, so ME design. Okay, ME design is 2.0. Then we need to understand. So the AE is not provided. Okay, so AE is not provided. So to find So what the problem is asking is to find the value of the back pressure, or the range of back pressures PB for which the nozzle is choked, which means to find PB critical for this converging diverging nozzle such that for PB smaller than PB critical, or smaller than or equal to PB critical, the nozzle is choked. Okay, choked. Also find mass flow rate m dot for PB, for two values of back pressure. So 450 kilopascal and 0 kilopascal. This is obviously going to be the choked case, and this is choked or not, I don't know yet. Okay, so now the solution to find PB critical, right? So to find PB critical, I need to know what the exit Mach number for the critical case is. And for the critical case in a converging diverging nozzle, as we know, it's not the supersonic flow case, right? It's the case where the Mach number of the throat is 1, and in the diverging section, the flow decelerates into a subsonic flow, and the pressure increases because of the compression. So to find this PB critical, we need the ME subsonic for choked flow, right? Choked flow, or basically what we are after is ME corresponding to case 4 in all our discussion diagrams. Okay, and how do you get that, right? So we know, all of you need to understand what a design Mach number is. Okay, when it says ME design is 2.0, so the design Mach number okay, so this is the Mach number at which nozzle operates at full capacity So it's the Mach number at which the nozzle operates at full capacity in isentropic fashion. Okay, which means ME equals 2 is the supersonic case, supersonic flow solution case. Okay, case. So if I know ME equals 2, then for gamma equals 1.4, I can use appendix B to get AE by AT, right? So this is choked flow, so AE by AT is the same as my AE by A star, because ME equals 2 can occur only when the flow is choked, and this is the case 5, okay? Supersonic, or let's call this as case 5 in your image that we, or in our graphic that we developed in the earlier lectures. Okay, so this corresponds to case 5. Then for gamma equals 1.4, you can use appendix B to get AE by AT, and this turns out to be 1.6875. And my PE by P naught for this case turns out to be 0.1278. Okay, these are values that I get from the tables. Now, what is my PB critical, or let me call it, okay? So my critical case corresponds to the subsonic solution or realized by AE by AT equals 1.6875. So what I'm saying is, in my critical case is the case when the flow is choked, the highest value of the back pressure for which the flow is choked, and that happens to be the subsonic flow case, or the subsonic choked flow case for this isentropic flow. And the way to obtain that is my AE by A, the flow is choked, so my AE by A star doesn't change, so it's still going to be 1.6875 for the subsonic case. So now I use use appendix B to find subsonic solution, okay? And this happens to be ME subsonic, which is basically the ME corresponding to the critical case, and that turns out to be 0.37 approximately, okay? So this is 0.37, and my corresponding PE by P naught and my PE by P naught for this case is going to be approximately 0.9, okay? And this is my PE by P naught. So, which means my PE subsonic choked equals 0.9 times P naught, okay? 0.9. Okay, let me write it different way. So this is PE sub by P naught into P naught divided by PE supersonic, right? I'm sorry. This is going to be P subsonic into P naught, and I know my P naught is 600 kilopascal, so this is going to be 0.9 into 600 kilopascal, which is 540 kilopascal, and this my PB critical is the same as the P subsonic choked flow exit pressure, which is 540 kilopascal, okay? Therefore, PB less than 540 kilopascal implies choked flow. Which implies that nozzle is choked for PB equals 450 kilopascal and 0 kilopascal, and that's what we are realizing. So now I know that the flow is choked for both the case where the PB is 450 kilopascal and 0 kilopascal, which means what is my part 2 of the question? Find m dot for PB equals 450 kilopascal and 0 kilopascal, which is, so the m dot is going to be what? Which is m dot choked, okay? So this is choked flow. So m dot choked is nothing but P naught AT, okay? So I already know my throat area, right? So in the choked flow, the Mach number at the throat is 1. So P naught AT by square root of R T naught square root of gamma times MT 1 plus gamma minus 1 by 2 mt squared minus gamma plus 1 by 2 into gamma minus 1, right? Okay, and mt equals 1, which implies that if I plug in the numbers, my m dot choked is going to be 1.08 okay, it's going to be 1.08 kilogram per second. Okay, this is my mass flow rate, and this is my maximum mass flow rate through this nozzle. Okay, so this is how you solve these kinds of problems. Obviously your homework is going to involve much more variety in the problems, so try to make an honest attempt at solving those problems, and obviously get back to me if you have any questions. Okay, thank you. And this concludes chapter 3.